Aloha! In this video, we discuss polyprotic acids. If you've seen how to deal with strong and weak acids already, then I think you'll find polyprotic acids not too much more difficult. Let's take for our example phosphoric acid, which is H3PO4. This is a triprotic acid. It can release 3 protons in solution for each molecule. And the way polyprotic acids work is the molecule releases the first proton, and the conjugate base that remains can go on and release the second proton, and the conjugate base from it can go on and release the third proton. Now, each one of these dissociations is a weak dissociation for phosphoric acid, and therefore has its own equilibrium constant. So this is the K for the first dissociation. We'll call it Ka1 since it's an acid and it's the first one. Ka2 is much smaller than Ka1, and Ka3 is the smallest of all. And that's what always happens. The first dissociation has the largest equilibrium constant. You get the most proton from it. And then the second and third dissociations, if there is one, the equilibrium constants are much smaller. You would get much less products from them. So the second and third dissociations occur to much less extent. If you look at the equilibrium constants, 10 to the minus 3 versus 10 to the minus 8, that's 5 orders of magnitude difference. And then 10 to the minus 8 to 10 to the minus 13, that's another 5 orders of magnitude difference. So those dissociations occur to much less extent and produce negligible proton concentration. The strategy that you should take when dealing with polyprotic acids, if you're looking for the pH, is to just ignore the second and third dissociations. So just consider the first one. To demonstrate that you can do that, we're going to work through the first one and the second one and the third one and see that we could have ignored the second and third one. So let's work through all 3 of these and see how that's done. The first dissociation is rewritten right here, and its equilibrium constant expression is right there. You're starting, if the problem is to find the pH of 1 molarity, H3PO4, that's a pretty concentrated solution. So the initial concentration of H3PO4 is 1 molarity. And you don't have any products at the beginning, ignoring autoionization of water. So you lose X amount of reactant and gain X amount of products, and those are your equilibrium concentrations. And you can plug those into the Ka expression right here and plug in the value for Ka1 that was given to you up there. And now this is the equation that you have to solve. I would not use the X's small approximation here because the equilibrium constant compared to the initial acid concentration, this is not 1,000 times bigger than that. It's somewhere between 100 and 1,000. It's probably better to solve this one exactly. And doing that, you get X equals 0.083 molarity. So that's the molarity of proton you get from the first dissociation. So the second dissociation we can think of as occurring after the first one is done. So after the first one is done, and you now have X amount of this left, that can go on and dissociate to produce more proton concentration. So you have to take the X that you calculate and plug it in, not only for the proton concentration that you now have, but also for the H2PO4 minus concentration that is available to dissociate. So these are the initial concentrations in the second dissociation, but you haven't yet generated any HPO4 minus 2. So now that you know your initial concentrations, you can fill out the rest of the ICE table. Similarly, We don't have any product here, so we still have to lose X amount there and gain X amount here and here. And those are now the equilibrium concentrations. And we can plug them into the Ka2 equation right there. And plugging in the value for Ka2, we're left with this nasty looking expression. Try solving that one for X exactly. Well, you can use the X's small approximation twice here. You're trying to add X to a large number and subtract X from a large number. And since the equilibrium constant is tiny, the amount of X that reacts, the X is the amount that reacts, that's going to be tiny compared to what you started with. So you can ignore it in both places, and look what happens. These numbers cancel. And so the X that you're solving for is simply equal to the equilibrium constant for the second dissociation. X is 6.2 times 10 to the minus 8. Now that's a negligible amount of proton that's generated in the second dissociation. So this is what's generated in the first dissociation. That's like 10 to the minus 2, and this is 10 to the minus 8. It's nothing. So you can neglect it if you're just looking for the pH. But let's go ahead and go through the third dissociation. There's something else that I want to point out. So you take what you generate from the second dissociation. So here's your proton concentration, as is now. It's what the first one gave you, and now plus X from the second one. And now you have X amount of this. So you take your proton concentration, and that becomes the initial proton concentration for the third dissociation, and you take the X for that, and that becomes the initial HPO4 minus 2 initial concentration there. Now the initial proton concentration, this is insignificant compared to that, so you can't really add that. That would add digits way out here, and it doesn't make sense. This is 0.083. And so it doesn't make sense to add that here, just ignore that. And so those are your initial concentrations. And so you lose X here and gain X there and there. And now you have the equilibrium concentrations. And finally, we can plug these into the Ka3 equation. And plugging in Ka3, you're left with that expression right there. Now you can use the X's small approximation twice again. When you do, these don't cancel as nicely as they did before, but it's still an easier equation to solve this time. And when you solve this for X, you get 3.14 times 10 to the minus 19. So that is a very small amount of proton generated in third dissociation. So you would have to add that to the proton that you started with. That wouldn't make sense. All of the proton that you generate is generated in the first dissociation for all significant purposes. Now the phosphate, on the other hand, that's simply X. So you've only generated X amount of phosphate. You didn't get phosphate anywhere else. Any of those other dissociations didn't give it to you. It's only the third one that gets you the phosphate. So that was my point for doing all three of these. If you're asked what the phosphate concentration is, you have to go through all three to get to it. But if you're asked for the proton concentration or just the pH, you only need to do the first dissociation. So the proton concentration is 0.083, which is what we got from the first one. And so you can plug that into the pH equation and calculate 1.08. Now you can, if you want, figure out what all the other concentrations are at equilibrium. We already said the phosphate concentration is that, and you can figure out the other ones. So, be on the lookout if you're dealing with polyprotic acids. Make sure, make sure you know what you're asked for. If you're asked for the phosphate concentrations, you have to go through all three. But hopefully, you're just going to be asked for the pH or something, so you can ignore the second and third dissociations. This is how you handle polyprotic acids. Almost all of them are like this, and it's only the first dissociation that you need to worry about, and that's because the equilibrium constants are usually much smaller for anything after the first one. The only case that I know of where you have to deal with the first and second one when you're looking for proton concentration is sulfuric acid. Sulfuric acid is one of the 6 strong acids, and it's a diprotic acid. That first proton comes off completely, and then the second one is a weak dissociation, but its Ka value is like 10 to the minus 2. So it's a pretty large Ka, and you should, account for it. So you should do the first one as a strong dissociation and do the second one as a weak one. We're not going to do sulfuric acid in this video, but you might see that as an example in your Gen Chem text, and I would read through that example. I think it's much easier to deal with than this one that we went through here. If you were able to follow this, that was quite a bit. You're doing pretty good. So this is a tough problem to go through all 3, but it's methodical. And in our next lecture, when we discuss mixtures of weak acids, we're going to solve those problems in a similar manner to the way we approached this one. So stay tuned for that. Aloha.